Right. So, which means we come to the talk that we've all been waiting for a couple of hours. Atle, you're are the last this session, but not the least interesting. One of the most interesting things, I believe. And
Well,
so go ahead and let us know what multiprocessing in force looks like in your spirit.
like an hour ago, I realized that Travis Beeman has already done what I've been trying to do, but I'll, I'll do it anyway. So I'll start off by showing what it is, and then I'll say something more about it afterwards. Um, can you see my screen now?
Yeah, we see it.
Okay, then I'll first go and tell you about a word. You're familiar with the execute word. Um, you take a quote and then the name of some fourth word, and then you execute it, right? Um, Now I have one called spawn that does exactly the same thing, but it spawns it as a background task. And to illustrate this, I have created a counter that counts to 100. So I'm going to spawn two of those. And now these will be scheduled to run by the operating system, which means that they're not doing anything as long as the process is suspended. But when the process is no longer suspended, then they start executing in the background. And you will see here that there are two of them that count to 100. Let's see if we can find, yeah, there should be duplicates of numbers. They should be chaotically printing numbers from 0 to 100. Yeah, there you see one is already finished, and there the other one is finished. So they are executing at the same time. And I did a prime, a sieve where I let tasks just run wild like this, but I got race conditions galore. So I needed some way to synchronize them. And for that, I created a queue. So a queue is something that you can write to. It has a size. This one is 26 bytes for some reason. And when you've written those 26 bytes to it, then it blocks. Whichever, if you have written and you try to read again, it will block. If you read it and it's empty, then it will block. So I imagine a robot that is racing down the highway. And then I'm checking, there's a word to check the speed. If it's less than 100, it should speed up. And if it's more than 120, it should slow down. There's also one for checking the direction. And then there is, since this is not a real world application, this this word here should be reading some sort of sensors. It, for example, from a compass or something. And then whenever it gets something, this cue should be fed by these sensors, and then it will check the direction. And the same for the speed. It will read this cue, and then it will check the speed. Now I spawn these two tasks, read direction and read speed, and they are now running in the background. And And we can print to, for example, the speed queue. There. And then it tells us to speed up. Then I have, and what happened then was that this word here would write to the speed queue. It would convert this to a string. For now, these queues can only handle strings. That will surely change. And it would call the word check speed, which is up here, and it will tell us to speed up because we're going too fast. So now I have a word drive that will simply increase the speed from 90 to 130, and I will start that in the background. So and now it tells it to speed up because it's going too slow. And while I'm doing that, I can continue programming here. I can continue defining words. It's a bit non-standard here. Please don't hang me for that. So now I can, oh, and now it's starting to slow down. It wasn't saying anything as long as the speed was within range, but now it's telling us to slow down because this word here is running in the background. It's increasing the speed and by writing to the speed queue. Imagine a microcontroller writing values to, like writing PWM values to motor controllers, for example. And so if it goes over 130, it will tell you to slow down, which it is now doing. And now it's finished. And all the time, these are still running, so we can still run programs here. That's more or less how it works. If there is time, I can show a little bit about what possessed me to do this. I'm gonna have to stop sharing and share another screen here. And then I got this one. Where am I now? Here. And then I have this one here. So what I heard when I was trying to research this, I heard about this green arrays, and I imagined something that could only communicate with its neighbors. I was thinking about FPGA and how difficult it is to make something totally interconnected. So I pictured something like this, and I wanted something like this. A fully interconnected network of 56 nodes, because I got 56 CPUs on my system. I asked an AI to draw that for me, but I'm not sure it understood me. So
That's Shay.
So what I have now is a fourth CPU. So whenever I call spawn, it takes the stack with it, it takes some housekeeping information with it, and it spawns it in a thread, in a Linux thread. and it still has access to all the I/O and memory of the original main thread. And I can have as many of these as I want, but as Travis pointed out to me, and as I realized before, is that if you have more of these tasks than you have CPUs in the system, you won't get any performance boost. And I had to Forrest Gump my way through this because I'm a total newbie in Forth. So I just did this the way a space alien would have done it. I have some central, I have split it up in built-ins. Those are the primitives, and some P codes because I couldn't interpret words. I needed to compile them into something more easy to handle, that would run faster, so I could just jump from one address to the other through a program, which I have here. And then when I want to run this, I combine a program and a task. So I run the program in that task. That's how I solved the multiprocessing thing. And this is the way it looks. So on top of the built-ins, I have the P codes, which also have semantics, and then the Forth sources out there, and I transform this as I go. And here are the central parts of the system. So I parse a Forth word into a P code, then I add that P code to a program, and then I connect that that program to a task, and then I let the runtime run this. And the runtime is what's being spawned. The runtime with this as parameters, that's being spawned. Some funny things. I tried to pass parameters on the stack until I realized that that's not possible. If you mess with a stack of independent tasks, you will break them completely. So I realized that I needed to communicate through queues to avoid these race conditions. And that's then I have a repo here where you can look at it, but it's not even alpha code. It's unfinished, and that's it. Now these queues, I realized when I had made them, because I wanted to make them fast, because I wanted this up and running fast as a proof of concept. I didn't really think about making something usable. I just wanted to play with it. But I realized that these queues, instead of giving them names, I can give them IP addresses and port references, so that I can distribute this over a network and have 1/4. If the Forth starts up and the first thing it does, it's open a queue and read its input from that queue, then I can have one on each of my PCs, and I can sit on this console and control all these running Forths. That's one thing about it. And then, of course, I need to implement enough of it so that it becomes usable. And that's what I had.
Nice. Yeah, thank you very much. Are there any questions?
Josh.
Yeah, sorry. I've also a scheme for multitasking, which uses preemptive multitasking, and it uses under Windows so-called APCs, that are asynchronous procedure calls. And if you are interested, and if there's time, I can show a little program for you.
Yeah, please do.
Okay, I will share my screen. Okay, yeah, okay. Okay. This is the program. It runs a Julia fractal, and in this case, it uses one thread. And if I swap the colors, you see it is taking 223 microseconds. If I use all the available threads on this PC, then you see it takes only 19 microseconds. And that is because all the threads are running all together at once, and they're all updating a bitmap in memory. And that is how I use the APCs.
Yeah, so you are also just copying the stack. You have one separate stack for each thread, right?
Yes, that's correct.
And these are threads and not processes.
Now,
So you still have access to the data.
sorry, Dave?
So do you still have access to all the main threads data from the spawn thread?
Well, now I have allocated a piece of memory in which I store the bitmap, and all the threads have access to that bitmap.
Yeah, okay. Yeah, then that's basically the same.
Okay. Even kijken. Zo. Oh, I'm looking for my screen.
The red one, the red button.
Atle, not the question, but did you explain what is the purpose of this project?
Well, what I wanted was this idea that my robot is in activity, it's doing something. And while it's doing something, I used an example of a car driving on a road. In reality, it would be my robot driving on the living room floor. Or it could be any other type of robot. But I wanted to program it as it was doing its business. And with single-threaded cooperative multitasking, I couldn't get that to work. So this is why I wanted this. I wanted to be able to just start off a task and have it read or write to queues to synchronize it, and I could have one for these types of sensors, another one for these types of sensors. So that's why I did this.
I follow Atle, and I talk a lot with Atle about robotics. We have also another expert in the group, which is Rob Probing of robotics. And the Milk 5 I bought is for use in robotics also. And Josh has shown the group a robotic arm not long ago, making some, it was, I can't remember the name, but Josh can explain us better. And I recommend that both Atle and Josh get in contact, stay in contact over email or over some other channel, because Josh has always helped me a lot. I use the examples of Josh from the Win32 force. He has a wonderful page with examples. And if you both are working with robotics, Josh will love to see what you are doing, Atle. Atle has a robot of 40 centimeters from China with servos, with lots of servos.
Oh, my background.
Okay.
These robots from High Wonder or so. Can you talk to the microphone, Atle? Again?
Yes, in a moment. I'll just put this back. Yeah, can you hear me?
You know, when you show the robot, because your image went.
Okay. Let me see. Let me. It's not easy to place it in a way that you can see it, but I think oh yeah, it's there and then it's gone. I would have to change my background in order to do this, but it's a kit available from AliExpress for about $70 or so.
And I am always, and I say that every time. Sorry that I repeat so much the same. But when I was a young engineer in the 20s, in my 20s, and I saw the Leo Brody starting force, they had the robot serving coffee and the vocabulary of how to serve coffee. And when I saw the robot of Atle, I saw this is perfect for force. And Atle has a Jetson Nano for machine vision, for robotic vision on this robot. And he wanted to implement over the Jetson Nano. This is the Jetson, yeah. He wanted to implement over the Jetson Nano a layer with G-force that would control the Jetson Nano, and or I don't know how he wanted to implement. I'm just talking like a stupid, because I don't know the details. But I understood he wants to make a force layer and to control more simple the Jetson Nano information. Is that correct?
Yes. Well, I need a hook into there's a neural network that runs and recognizes objects, and it produces a value, a string for the object that it has detected, and then I could pick that out and feed it into Forth, so that Forth could then run like a sort of a knowledge base that would know what to do with each of these symbols that came in from the neural net. So it would be more like a communication between different systems. It could all be implemented on the Jetson Nano.
For me, it was really interesting because I never saw any kind of works similar to this. It's pioneer work, and it may spark the interest of young engineers, other people who are working very hard in robotics. And so I recommend stay in contact with Josh. Maybe he has some interesting ideas, and keep keep with your work because it's super interesting.
Well, thanks. I'm getting a little bit confused with all this. I don't want to use Python. I want to have the C libraries containing what I need and nothing more. And there's a jungle out there of stuff. So finding my way in that is the biggest challenge.
You see, Christian has a question.
Oh, Christian.
I always forget my microphone. Atle, I enjoyed your presentation, but I got stuck on one expression in there, P-code. What is it?
It's something that dates back to the days of UCSD Pascal. It's really because I was caught up in this, all these people who wanted to build a fourth CPU. And then I remember this project from way back when, where I was supposed to build a Pascal compiler that would compile to P codes, and those P codes would be running on a P machine.
Yeah, just
Java
like
has
Java,
the same thing.
Just like Java bytecode.
exactly like Java bytecodes.
Yeah.
Yes, and
Uh,
I said to Atle privately, not now, another opportunity, that Chuck invented P code much earlier because our P code are the tokens of force,
Exactly.
and we
The
have Chuck in the meeting. Do you want to ask to Chuck if he was first?
Well, it would be nice to hear his comment. Chuck, are you there?
I forgot my.
I think
no,
he
that's
went-
too long ago. I don't recall the context.
The last time I heard the expression P code was when I built my Apple II clone. I think they
Well,
were using some.
there was a UCSD Pascal for Apple. I had one of those.
But more or less it's a form of portable code.
Well, it's what it is. If you have a pure interpreter, then you have to check. You have to process strings all the time. If it is it this word, is it this word, is it this word, and if it's this word, then you have to branch off. When you compile this to P codes, then all you have to do is jump from one address to another one to another one. You can have this arranged in tables. So the execution is much faster. I had a race with GeForce here that wasn't entirely fair because probably my I/O is a lot faster, but it was really fast.
So you're using a kind of table that is indexed by a number that corresponds to a word.
It's a pseudo machine code. I guess that's
It's
maybe what.
Christian, it's just tokens like we use in
Token
force. But
tokens.
Atle wanted to say something from another language, and we speak
Okay.
force here.
But
Yeah, well,
that
P is
code
actually
subjected to
Pascal.
some virtual machine.
P is actually for Pascal. Niklas Wirth used it for aiding the porting the Pascal compiler to different machines. So you only have to implement the interpretation of the code, and then you are done, which is much easier to have a native code generator. And yeah, the idea is the same, but the name, of course, P code is based from Niklas Wirth, and it has a very specific purpose at that time. Yeah.
Okay, but it doesn't mean that Pascal was used in that project.
It only
There's a
means
name
that
to code.
it only means that I'm a bit I'm a bit geriatric. That's the only thing it means.
Yeah, I mean,
Okay.
Microsoft did use it to mean portable code machine, but that was really a corruption of Nicholas's original concept, I think.
Okay.
Yeah.
Thank you, Atle.
Yeah.
I think
I
Chuck's invention was first. Who was first?
Yeah. Is it important?
Then Atle, we need to excommunicate you. There is no other solution. Atle wanted to start a meeting with a Java explanation. I said, Atle, please, never start in a force.
That's the real story of how it started. But Peter told me you cannot tell them this.
But to say something in favor and try to bring him back to our force speech, I am impressed with Atle because he brings such interesting ideas and he's able to discuss these ideas from different angles, from his knowledge in Java and from his knowledge in Pascal and etc. And it's always very, very interesting to discuss with him different problems of programming.
But just
Yes,
to
well,
add to what
let's yeah, P code machine, yeah, P code for a hypothetical central processing unit, exactly. Same as the MATLAB does it as well. Oh yeah.
It was also copied by Bill Gates in the Quick Basic.
Yeah, there were some compiled basics, yeah.
Yeah, but these are like 10 or 15 years after Chuck and Nicholas were doing their work in the 70s, right? I mean, the thing is that people take old ideas and go, that was a good idea, let's reuse it. You know? I mean, the first reference on that page that I posted was 2016 in a book about Raspberry Pi. But I mean, it's like 40 years. I don't know where that when I think it was wasn't it the guy wrote it was, yeah, I mean the guy who wrote the book might not have been, I don't know whether Eben was alive at that point, right? I mean, people forget, things get corrupted. I mean, it's good, it's reusing ideas.
Well, in any case, back then, to me, Fort was just some magic you could get for the ZX81. That was all I knew about it.
And then half of the characters that Forge depends on are not even in the character set of the ZX81. You have to use funny graphic blocks instead of store and fetch and
The fourth ROM. I really regret I didn't buy that.
Okay, you had this dedicated Ford ROM. But there were Fords that had to use stupid substitutions like this and this graphics block represents the the store character or the fetch character or whatever you have, because these weren't in the character ROM of the ZX81. Really stupid.
Yeah.
And then you had the Joopy. I like the idea a lot. I haven't never owned one.